Hey everybody, today what we're going to do is start talking about calculus and how it relates to simple harmonic motion. Let's see if I can find a place to put this. It won't be completely, okay. This is new. All right, so first off, some useful things that are on the AP equation sheet for you, and that is on side 2. It tells you what the derivative of cosine and what the derivative of sine are. So finding the derivative of cosine will give you a negative a sine x, if we have the cosine of ax, and figuring out the derivative of sine of ax gives you a cosine ax. So since our equation is x is equal to a cosine omega t, if we're going to use calculus to figure out speed and acceleration from that, we know that speed is dx dt. So if we take the derivative of x with respect to time, we're going to have a, and then the omega is going to come out, and then sine of omega t. So that's just using this one up here. And to find the acceleration, we take the derivative of speed. So that's going to be a negative a omega sine omega t. So if we take the derivative of that, we get another a, which is omega in this case. That's going to give us a negative a omega squared cosine omega t. And so when we're looking for velocity, that's all you got to do, is take the derivative. And that also tells us that the maximum velocity that we've got has got to be this a omega. So if we wanted to find Vmax, if our equation of motion was x is equal to 5 cosine 2 pi t with a mass of 3 kilograms, we know that speed is dx dt. So if we take the derivative, it's going to be 5 times 2 pi times a negative sine 2 pi t. It's equal to negative 10 pi sine of 2 pi t. But we know that the maximum value is going to happen where the sine is equal to 1. Sine can only go between 1 and negative 1, and that's it. That's all we got. So if we're looking for the maximum value, then we just set the sine part equal to the biggest value it can get to, which is 1. And that's going to give us 10 pi, or 31.4 meters per second. So that's one way to find Vmax. We talked about other ways to do that using energy yesterday. All right, so acceleration. We know that the acceleration is equal to the derivative, the first derivative with respect to speed, or with respect to time of speed, or it's the second derivative of x with respect to time. So either way you want to go. So if we take the derivative of a omega sine omega t, and then take the derivative of that using our handy dandy equation from the AP sheet, we're going to get a negative a omega squared cosine omega t. So with that same equation that we had in the previous example, if we take dv dt, that's going to give us a negative 10 times pi times another 2 pi times now cosine of pi t. So that's going to give us a negative 20 pi squared cosine 2 pi t. And if we want to find the maximum value, again, that's going to happen where cosine is equal to 1. So if we replace cosine with 1, then that gives us 20 pi squared, and that's 197 meters per second squared. APC is okay if you leave things with pi in them, but oftentimes we want to get a number, so if we just multiply it out, that's good. You'll notice I didn't leave the negative on either one of these. That's because we're looking for the maximum value. So we know that it's going to go, it's a sinusoidal function that's going to go between a max and negative a max. So whether you give a positive or negative value here, it's still going to be the amplitude of that motion. And way back when we first started talking about simple harmonic motion, we kind of reasoned through what these graphs were going to look like. So if we start our spring stretched out, then it's going to have a positive amplitude. It's going to go through the middle through equilibrium. Then it's going to squash in and have a negative amplitude. Then it's equilibrium, stretch out, and so on. Speed is going to do just the opposite. That speed is going to start from rest because we're just holding it there at its biggest amplitude. It's going to go fastest when it's in equilibrium, so right here, and it's going to go 0 when it goes through equilibrium again, and then it's going to go fastest when it goes through, it's going to go 0 when it's all the way squished in, and then it's going to go fastest when it gets back to equilibrium again, and then it's going to be stopped when it stretches out again. But it's a negative relationship, negative sign, because if this is stretched out, then it wants to move in the negative direction because it wants to squash in. And if this is squashed in, it wants to move in the positive direction in order to stretch out. So that's why it's a negative sine curve. And with acceleration, wherever we have the biggest acceleration or the biggest force is where we're going to have the biggest acceleration. And that's where it's stretched out or where it's compressed. So here it's stretched out, here it's compressed, but it's a restorative force. So if it's stretched out, the force wants to move in the negative direction to compress it in. So it's a negative acceleration or negative force. And here, if we're going to be all the way squashed in, it wants to stretch out, which is why it's moving, it's accelerating in the positive direction, and therefore a positive acceleration. So just some other examples of position, velocity, acceleration, and force. You notice that the force is exactly the same as the acceleration graph because force is equal to ma in addition to being equal to kx, or negative kx, which is why this is a negative cosine function compared to x. So if we were to take a look at an example, so the displacement of an object undergoing simple harmonic motion is given by the equation x as a function of time is 3 cosine 8 pi t plus pi over 4, so that's that phase angle, you remember. Amplitude is just going to be whatever is in front of the cosine, so we know that that's going to be 3 meters. Frequency is going to be, this is omega, and omega is equal to 2 pi f. So if we divide by 2 pi, that gives us 4 hertz. And then if we want to know position, velocity, and acceleration of the object at t equals 0, then we do some derivatives. So we have x at 0 is just going to be 3 cosine of pi over 4. You know, just plugging in, if that's 0, then this is going to be pi over 4. That's going to give us 2.12 meters. The trick, something just to note, is that you have to be in radian mode. Pretty much everything else we do in physics, you need to be in degree mode, but not this. This is the one thing that you need to be in radian mode if you are getting a number. It's okay typically to leave this as cosine of pi over 4, but sometimes it's good to get a number. To get v, we're going to take the negative derivative of this, or we're going to take the derivative of x of t, and that's going to be the negative sign, and then just make sure you multiply by the 8 pi, since that's omega. This part here does not factor in because it's not attached to a t, so you don't need to worry about that. It's just a constant. So we've got negative 3 times 8 pi times the sine of pi over 4, that's a negative 53.3 meters per second, and acceleration is the derivative of this one. And don't forget the 8 pi. So there we've got negative 3 8 pi squared cosine of pi over 4. And that gives us a negative 1340 meters per second squared. If we were then asked to figure out what the force was, as long as we had the mass of our object, we would just multiply that by whatever A is. All right, so now we're going to move on to the next phase, which is talking about getting the period of the spring oscillation, or the period of any kind of oscillation, and that is looking at a differential equation. So yay! We'll do differential equations after simple harmonic motion. We'll do a little bit more. We didn't do drag in the fall, so we'll do that this spring as well. All right, so Hooke's law is that the force is equal to a negative kx, and the negative is important here. That negative really only is important when we're doing calculus because it's directional, and that directional part really matters. When we're doing free body diagrams and stuff, the negative doesn't matter because we're doing a free body diagram that shows direction. So if we have one force that's going up, like the spring force going up and weight going down, that negative sign just sort of comes out in the wash because they're pointed in different directions. But if you're doing things mathematically with calculus, that negative sign needs to be in there because you can't see the direction. So the spring constant is, it's a constant, it's newtons per meter. That's wrong, it's newtons per meter. X is the displacement from where its relaxed state is, which is the equilibrium position. And then don't forget that we have two equations for force. Not only do we have force is equal to negative kx, but we also have force is equal to ma. So if we set those two forces equal to each other, that tells us that we have negative kx is equal to negative ma, which is awesome. So then the next step is to write our differential equation. When you're writing an equation, you want everything in terms of one variable. In this case, we have x, but over here we have a. So we have to find a way to write a in terms of x. And we can do that taking derivatives. So if we have dv dt is our a, and we take the derivative of that, which is dx dt, then we get the second derivative of x with respect to time, and that's what acceleration is. So we have an x here, and we have an x here. So now what we do is instead of writing a, we put this in our equation. And there it is. There's our differential equation. This right here is usually worth at least, like if you can get this far on a question where they ask you to write a second order differential equation, you're getting probably, 20 to 40% of the points because this is huge, being able to set up this equation. It may even be more than that. So now we just rearrange it. So we're going to put it in a different form so that we get the derivative part by itself. That's always going to be the case with differential equations. We're going to get the derivative part by itself and then put everything else on the other side. So you can see that we have second derivative of x with respect to time is going to be equal to negative k over mx. So this is the equation of motion for mass on a spring. It's a second order differential equation. Woohoo! All right, so that was our equation up there. I'm going to try and move that somewhere so that it's not quite in the way as much. There we go. So solutions to these differential equations are unique, meaning there's only one. And the usual method of solving them is guess and check. Really, it is, which is amazing. And because we have this equation on our AP sheet that x is equal to a cosine omega t plus b, why don't we guess that one? Because, that's probably a safe bet. So if we plug those in, so if we take the second derivative of our x, we're going to get negative a omega squared is equal to cosine omega t, just what we were talking about before. And as long as, so if we plug that in, we have negative omega squared a cosine omega t, and then this side is negative k over m, and then a cosine omega t, so just our x. So the cosine omega t's, those will cancel out, the a's will cancel out. So as long as omega squared is equal to k over m, we're good to go. So in summary, the general form of our simple harmonic motion for a spring looks like this. The solution looks like this. Amazing how we guessed right the first try. So we have the second derivative plus omega squared x is equal to 0, and that's our equation. And omega squared is equal to the square root of whatever is over here. So, or omega is equal to the square root of whatever is over here in this type of equation. And that's an important piece of information that I'm going to talk about for a little bit more. There we go. So if you remember, the general form of the quadratic equation is ax squared plus bx plus c is equal to 0. So whenever you need to solve a quadratic function using the quadratic equation, you always have to get it into this form so that you know what a is, and you know what b is, and you know what c is, so you can plug it into this equation. The second order differential equation for springs is no different. So the general form, we want it like this. So just like it was ax squared plus bx plus c is equal to 0, we're going to rearrange everything so that it's the second derivative without any coefficients in front of it, plus whatever else is left in front of the x is equal to 0. And then omega squared is equal to whatever is in front of the x, just like b is the term in front of the x term of a quadratic function. So you get it in this form, and then you get what omega squared is by just looking at your equation. Okay, so in this equation, that means that omega squared is equal to k over m. So if we take the square root of both sides, omega is equal to the square root of k over m. But then, if you wanted to find the period, you use the equation that's on your AP sheet, that the period is equal to 2 pi over omega. So that's 2 pi is times 1 over square root of k over m. And if you're dividing by fraction, you multiply by its reciprocal. So that means we have period is equal to 2 pi square root of m over k, which is what we're using on the spring simple harmonic or simple harmonics motion spring lab. So that's where that equation comes from. It comes from setting up our differential equation. Omega has to be whatever term is in front of the x, as long as there's no coefficient in front of this, and we set it equal to 0. So let's do a little practice. So if I have a couple of equations here, I have second derivative of y with respect to t plus 4y is equal to 0, what would omega be? There we go. It's really that easy. Take the square root of whatever is in front of the original term here. And our equation of motion is going to be a cosine function. So y is equal to y max cosine omega t plus whatever phase angle we have. This next one is an actual physics equation. If you take electricity and magnetism, which is usually second semester physics in college, then this is an equation that you'll likely become familiar with. In order to figure out what omega is, we have to rearrange this. Notice that I is our variable because it's the second derivative of I with respect to time. This stands for inductance in a LC circuit, which you don't need to worry about. But that's our variable is the I. We're going to rearrange it so that there's no coefficients in front of this in front of the second derivative, which means dividing both sides by L, and then it's going to be a 1 over LC times I is going to be omega squared, so omega squared is equal to square root of 1 over LC. And our equation is going to be I equals I max cosine omega t plus b. So now let's take a look at the simple pendulum. Here we've got a string. So that's basically all a pendulum is you have a string and a mass. The string has no mass. So that's what a simple pendulum is. It's just a mass hanging from a massless string. And the pivot point is going to be wherever you've attached your spring or your string. And what's going to cause the rotation that it's going to have back and forth, what's going to cause that torque is a component of the mass. So the weight that's pushing down. So I've got my mass on a string. My force is mg. That's the only force I've got acting here. And because it's rotating, instead of dealing with forces, I'm going to be dealing with torques. Torque is equal to R cross F. So that's going to be my lever arm distance. I'm going to call L. That's the length of my pendulum. The force that's causing the torque is mg. And then I need the sine of the angle in between those two, which is that theta on my drawing. I also know that the sum of the torques is equal to I alpha. Now, if you look at this, you notice that this is really similar to what we did with springs, where we had our forces were equal to ma. Here we have torque is equal to I alpha. So I've got my torque, which is Lm g sine theta, is equal to a negative I alpha. And you might be wondering, okay, where did that negative come from? Well, it's because it's a restorative force. When I pull this to the right, my force pulls to the left. And when my mass is up here and the weight is pulling to the right, or is going downwards, my acceleration is going to be going the other direction. So it's a restorative force, and therefore we stick a negative sign on there, and that negative sign is really important, and it's really, really, really easy to forget. So we're going to start there. We have then that equation, L m g sine theta is equal to negative I alpha. So alpha is going to be d omega dt, which is the derivative of the derivative of d theta dt. So we get a second order differential or derivative for alpha. The other thing that we have, remember I was rotational inertia. For a point particle, that's equal to mr squared, which in this case is going to be L squared. So we have a point mass in the end of a string. Our I is going to be ml squared. So sum of mr squareds, it's going to be an ml squared. So if I substitute those in, so I have L mg sine theta is equal to negative ml squared, second derivative of theta with respect to time. And I now have a differential equation, but I need to get that in the form that we were talking about before, but I have this weird sign thing going on. So what we use is called the small angle approximation. So theta is equal to sine of theta for small theta. Which is pretty cool. That means that we have L, M, G, theta is equal to a negative ml squared, second derivative with respect to time. And now we want to get this in the form where we have the second derivative by itself, no coefficients in front of it, which means I'm dividing both sides by an ml squared, plus, so that's going to give me an L mg divided by ml squared theta. We got some L's that are canceling, m that's canceling, that equals 0. So then my ultimate equation is going to be this. Second derivative with respect to time plus g over L theta is equal to 0. My equation is going to be theta as a function of time is equal to theta max cosine theta or cosine omega t plus b. And then omega is going to be equal to the square root of g over L. And that's where that all comes from. So just to recap, we start with, we go back to torque. So Lm, our force, times the distance, the lever arm distance, times the sine of the angle between them, is equal to a negative I alpha. The negative was there because it's a restorative force. We can rewrite alpha in terms of theta, which is what the rest of our equation is in, using derivatives. So the second derivative of theta with respect to time is equal to alpha. Because we're talking about a point particle, I is equal to ml squared, so mr squared, but it's L, so that's why the L is there. And now we substitute in. So I have LmG sine theta is equal to a negative ml squared, because that's what I is. And then alpha is second derivative of theta with respect to time. Now we make the small angle approximation, that theta is about the same as sine theta for small thetas. We're talking about like 10 degrees-ish, somewhere in that range. So LmG theta, because we can replace the sine with a theta, is equal to negative ml squared, second derivative. We rearrange this to put it in the good format. So we divide both sides so that we don't have any coefficients in front of the derivatives. So the second derivative all by itself, rearrange stuff so that it's adding instead of subtracting, and that's going to end up with this equation. So let's do that. So our differential equation is going to look like this, which leads us to the answer that we've guessed and checked, which looks very similar to the one that's on your AP sheet for springs. And that tells us also what omega has to be. That omega has to be the square root of g over L, because that's the term that's in front of this theta. And we know that this has to be cosine because it'll work. Okay. Oops. Okay, there we go. So omega was equal to g over L, which means that our period is equal to 2 pi over omega. So our period is equal to 2 pi square root of L over G. So when we divide by omega, those are going to flip. So you're getting a sneak preview as to what the period of a simple pendulum is, which is what we're going to get to next week. So the next step is the physical pendulum. So we use the same small angle approximation as the simple pendulum. I is going to be different though, because I is going to be now a physical pendulum just means it's something that has mass. So it's not like a massless string and then a point mass. It's going to be something like if you drilled a hole in the top of a pie plate and set it rotating back and forth, or if you hook a meter stick on the edge of a hook and get it swinging back and forth. Because it's the whole thing has mass, that's a physical pendulum. So I is going to be something else. You know, if it's a sphere that's going, it might be like 2/5 mr squared, or if it's a rod rotating about an end, it'll be 1/3 ml squared, or something like that. L is the distance from the pivot to the center of mass. So now we have to worry about where the center of mass is, because that's where the mg is going to be acting, is at the center of mass, which if it's a point mass, like with the simple pendulum, that's where it acts, is right at the end where the point mass is. But otherwise it's going to act at the center of mass. If it's uniform, that means it'll be right in the middle. So you write the differential equation just like for the simple pendulum, and then you find omega and then t. So just like for the simple pendulum. So we're going to talk a little bit about I and review a little bit. You remember I? So when we had a point mass, it was mr squared. We just talked about that. We also had the parallel axis theorem that we could use. So that was I is equal to the I of the center of mass plus md squared, where d is the distance. The pivot is from the center of mass. And remember when we had a uniform rod or a shape that had some sort of weird density function, we could use this equation for I. it was the integral of r squared dm. So if we write this as dm is equal to m over L dr for a uniform rod, so if you remember, we set that up as a proportion, m over L is equal to dm over dr, and then that gets us here. Or you could have a density function. So the density function dm is equal to the density function dr. So if it's not a uniform thing, then you could have an equation here. For this particular type of problem, it'll always be uniform because it makes it a really ugly differential equation that is not solvable very easily if you have powers in here, so it won't be. It'll just be like m over L. And then for limits of integration, you imagine an L length number line where the pivot is at 0, and then the limits are on either side. So we're going to go through a couple of examples. So if the center of mass of a disk is 1/2 mr squared, using the parallel axis theorem, the edge of this disk is going to be a radius away from the center of mass. So that means we've got 1/2 mr squared plus mr squared, so that's the md squared, but d is the radius. And if we add the two of those together, we get 3/2 mr squared. So that's using the parallel axis theorem. And if we have a uniform rod rotating about a point 1/4 the way down, we're going to use I is equal to r squared dm integral. dm is going to be equal to m over L dr. I'm going to replace all the r's with x's because I like x more. So that means we have I is equal to x squared m over L dx. So I've just replaced the dm with this function right here. So I can take the m over L outside the integral because it's just a constant. So then I have x squared dx, which is not a hard integral to do. We know that's going to be x cubed over 3. So the next thing we need to do is our limits of integration and then some algebra, figuring out our answer. So the limits of integration, if our pivot point is at 0, then thinking of that as a number line, we're 1/4 the way to the left of that, which is a negative L over 4. And we're 3/4 the way to the right of that, which is 3L over 4. So that's going to be our limits of integration. And now we do it. And there's lots of algebra. Fun, fun, fun. So we've got m over L and then x cubed over 3. We plugged all that stuff in. And there it all is. And you do more with that, and it ends up being 7ml squared over 48. And if you want to pause it and follow all that algebra, you can. But I'm not going to go through that in a lot of detail. So now let's go through a physical pendulum example. So you use the same small angle approximation as you do for the simple pendulum. I is about the pivot point. There's a minus sign since the force is restorative. L is the distance from the pivot to the center of mass. So the center of mass is going to be the center of our circle, which means that our L distance here is going to be R. We write the differential equation just like we did for the simple pendulum. We find omega, and then we find t. All right, so we start with torque is equal to negative I alpha. All right, so that's going to be mg times r sine theta. That's our torque. Is equal to our I. In this case, we just figured it out. I is going to be 3/2 mr squared. And then alpha is going to be our second derivative of theta with respect to time. So I'm just starting with our torque equation. So torque equals negative I alpha. And I'm plugging in for I. I'm plugging in for torque. I'm plugging in for angular acceleration. That's the part that needs to be the derivatives. So since this is a sine, since we have a sine right here, we want to have since this is a theta right here, we want to have theta over here, which is why it's a second derivative. So then the next step is the small angle approximation. So that for small angle, theta is approximately equal to sine theta. So that gives me mgr theta is equal to a negative 3/2 mr squared, second derivative with respect to time of theta. So now we need to put it in the good form. So we're going to rearrange it so that the second derivative of theta with respect to time is all by itself, and we're adding instead of subtracting. We're setting it equal to 0. So we're going to have second derivative of theta with respect to time plus, if we rearrange all that stuff, we're going to end up with 2g over 3r. And if you want to pause the video and just check and see if that's what you get, when everything cancels and you're rearranged, that means that our solution doesn't change. It's still going to be theta max cosine omega t plus v, where omega is equal to the square root of 2g over 3r. Then if you need to find t, t is equal to 2 pi over omega, which will give you 2 pi times the square root of 3r over 2g. And you'll notice that this is really similar to the simple pendulum. The simple pendulum was L over G in that square root. This is different because we don't have a mass on the end of a string. It's a different I, so that's why it's a different period. AP likes to give you physical pendulum problems because they have they're just fun, and they have a lot of I in them. They have a lot of good stuff in them. Things, you know, the rotational stuff, and it's got this simple harmonic motion stuff. So this is probably the hardest thing at the end of the year to do is the physical pendulum, but it does review some of the stuff from rotational motion, you know, with the torque equals I alpha, and a little bit of I stuff. So if you have any questions with that, please come see me. We'll spend some time in class next week going over these as well and practicing.